In this lecture, we're going to be looking at the double angle and half angle formulas. There are trigonometric identities that involve the sine, cosine of double of an angle, as well as for half of an angle. The double angle formulas are as follows. The sine of 2 theta is always equal to 2 sine of theta cosine of theta. Notice how the double angle formulas rewrite a trig function of twice an angle as a trig function or combination of trig functions of just the angle itself. So this would say we could figure out the trig function value for an angle that's twice as big by knowing the two angles, or the angle, I guess, that you've doubled to get to that size. Cosine of 2 theta is always equal to cosine squared of theta minus sine squared of theta. Notice how similar that is to the Pythagorean identity, only instead of a plus in between, there's a minus. So cosine squared minus sine squared is always equal to cosine of 2 theta. Alternatively, there are two other formulas for cosine of 2 theta, which come from the Pythagorean identity, as we will demonstrate shortly. You can also rewrite this as 1 minus 2 sine squared of theta, and cosine of 2 theta is also 2 cosine squared of theta, all minus 1. Not theta minus 1, but the whole 2 cosine squared of theta minus 1. Now, let's start with, say, the first one. Why is sine of 2 theta equal to 2 cosine, 2 sine theta, 2 cosine? Let me say that right. Why is sine of 2 theta equal to 2 sine of theta cosine theta? And all you have to do to show this is to recall the sum formula. Remember that sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta. Now, if I think of 2 theta as sine of theta plus theta, that means, which theta plus theta is 2 theta. If I just split that up and make it a sum of 2 angles, I can rewrite this as sine of the first angle, which is theta, cosine of the second angle, which is theta, plus cosine theta sine theta. But notice cosine theta sine theta is the same thing as sine theta cosine theta, so I get 2 sine theta cosine theta. Now for the next one, same approach. Remember that cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta, which we proved earlier. So cosine of 2 theta could be thought of as cosine of theta plus theta, which would be cosine of theta minus sine theta, which gives us cosine squared of theta minus sine squared of theta. So cosine of 2 theta is always equal to cosine squared of theta minus sine squared of theta. Proved. To see where the other cosine of 2 theta identities come from, the other double angle identity for cosine, all you got to do is recall the Pythagorean identity. That is, that sine squared of theta plus cosine squared of theta is equal to 1. Now, if I take this sine square, actually, I tell you what, let's take the cosine. I'll take the sine squared to the other side. Boom, like this. So cosine squared would be 1 minus sine squared of theta, right? So now we're going to substitute that into this earlier identity here. Namely, if we start with cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta, which we just proved, and replace cosine squared with 1 minus sine squared. Like that. Then, now since there's only a 1 in front of those parentheses, we can drop those parentheses, and you're left with a 1 minus 2 of these sine squareds of theta, which is exactly what we were wishing to show. And for this last one, simply use the same procedure, only now instead of saying that cosine squared is 1 minus sine squared, we take the Pythagorean identity and show that sine squared of theta would be 1 minus cosine squared of theta, simply by moving cosine squared to the other side, subtracting it from both sides. Then this earlier identity, cosine of 2 theta equals the cosine squared of theta minus the sine squared of theta, becomes, and again all we're doing is substituting, cosine squared of theta minus, and all of sine squared theta is now 1 minus cosine squared of theta. Now put the parentheses there to emphasize that I'm subtracting all of it, which means I have to remember to distribute my negative. So this becomes cosine squared of theta minus 1 plus cosine squared of theta, which is 2 cosine squared of theta minus 1. Proved. In this example, we are provided the value of the sine of theta to be 3/5. We don't know what the angle is, and in fact, we're not even asked to find the angle theta. We just know that the sine of it is 3/5, and that the range in which you find theta is between 0 or pi over 2 and pi, which means it's in the second quadrant. It's somewhere up here, right? Now, if it's up here and we wanted to find sine of 2 theta and cosine of 2 theta, we're going to need to know cosine of theta as well, right? Because sine of 2 theta is 2 sine theta cosine theta. So we need to know what cosine theta is. We already know what sine theta is. So what's interesting again about this example is that you're able to find the trig function values for a double angle that is twice as large as the theta just from knowing information about theta. So if sine of theta is 3/5, then we'll let the 3 be the y, as we have done in the past, and the 5 be the r. So x squared plus y squared equals r squared means x squared plus 3 squared is equal to 5 squared, which means x squared is equal to 25 minus 9, or 16. So x is going to be -4. You take the square root of both sides, and you know it's negative because you're on the negative x-axis in quadrant 2, which means that cosine of theta will be -4 over 5. With that information, we can see that sine of 2 theta would be 2 times sine of theta from here is 3/5 times cosine of theta from here, which is -4/5. So we get 2 times 3, which is 6, times -4 is -24 over 25. There is your sine of the double angle. Now to do cosine of the double angle, cosine of 2 theta, you can use any one of the 3 formulas that we've got. Let's use cosine squared of theta minus sine squared of theta, which gives us a -4/5 squared minus a 3/5 squared. So that's 16/25 minus 9/25, which gives me 7/25. Done. In this example, we are asked to establish the identity tangent of 2 theta equals 2 tangent of theta minus tangent squared of theta. Two approaches come to mind. One, we could go back and rewrite tangent of 2 theta as sine of 2 theta over cosine of 2 theta and try to work with that. Or we can use the same process that we used above. I'm going to scroll up, that we used, for example, here, and that we used here, in simply going back to the sum formulas. In this case, for tangent, recall that tangent of alpha plus beta is tangent of alpha plus tangent of beta over 1 minus tangent alpha tangent beta. That is the sum formula for tangents that we looked at in the previous lecture. So tangent of 2 theta would be tangent of theta plus theta. And now I'm just going to use, everywhere there's an alpha, put theta. Everywhere there's a beta, put theta. Tangent of theta plus tangent of theta divided by 1 minus tangent theta, which gives me 2 tangent theta on top and 1 minus tangent squared of theta on bottom, which is exactly what I was trying to prove. Done. In this example, we are asked to establish the identity sine of 3 theta equals 3 sine theta cosine squared of theta minus sine cubed of theta. Let's follow a similar approach to what we've done in previous examples. Let's start with the side with sine of 3 theta and recognize that this would be the same thing as sine of theta plus 2 theta. Now apply the sum formula for sine. Sine of theta cosine of 2 theta plus cosine of theta sine of 2 theta. Now for these, let's use the double angle formulas that we already have. For example, we have cosine of 2 theta is cosine squared of theta minus sine squared of theta. And sine of 2 theta, recall, is 2 sine theta cosine theta. So this becomes sine of theta times cosine squared of theta minus sine squared of theta plus this cosine theta here times a 2 sine theta cosine theta. Multiplying everything out gives me a sine theta cosine squared of theta minus a sine cubed of theta plus a 2 sine theta cosine squared of theta. Now this term here and this term here are like terms, so I end up with 3 sine theta cosine squared of theta minus sine cubed of theta. Proved. In addition to double angle formulas, we also have a set of formulas called half angle formulas. In fact, we can rewrite the double angle formulas from cosine into the following form. Recall that cosine of 2 theta is 2 cosine squared of theta minus 1, or it could be 1 minus 2 sine squared of theta. And for both of these examples, what you can do is you can take this one right here and solve for cosine squared of theta. Solve for this right here. In other words, you would take this 1 and move it to the other side and then divide the 2 across. You end up with, when you do that, this right here. You end up with a 1 plus cosine of 2 theta, all divided by 2. On the other hand, if you take the second one and move the 1 to the other side and divide both sides by negative 2, in other words, solve for sine squared of theta, you end up with this right here. And lastly, if you take these two formulas here and divide them, if you do sine squared of theta minus cosine squared of theta, which of course is tangent squared of theta, you'd have 1 minus cosine of 2 theta over 2 divided by 1 plus cosine of 2 theta divided by 2. If you invert and multiply, these twos end up canceling, and you're left with this guy right here. Now, how are those useful to us? Well, notice the relationship between the angles on each side of these formulas. The angle on this side now is half the size of the angle on the right-hand side in all three cases. Right? The angle on the left is half of the angle on the right. So if instead of putting a 2 theta here and a theta here, if I put an alpha here and then half of that alpha over here, that formula would still be equivalent. It still means the same thing. If I put an alpha here and an alpha over 2 here, if I put an alpha here and an alpha over 2 there, and then take the square root of both sides, all of these formulas here become what are known as the half angle formulas. So again, take the square root of both sides and let 2 theta be alpha, then theta simply becomes alpha over 2, and we have these formulas right here. One additional note here, the sign, S-I-G-N, of the half angle formula is determined by the quadrant the angle is in. Right? So when you do a plus or minus, you have to figure out, well, is that sign going to be positive or negative? And you look at that based on what quadrant your half angle is in. And we'll see that in a couple of examples. Here are a couple of angles for which we, actually three, that we can use our half angle formulas to find the exact value. We don't have to approximate with a decimal in our calculator. We will get the exact value if we can recognize the fact that these angles are actually half of some known angle. That is an angle that we can find the trig function values for. In this case, sine of 22.5 is half of 45 degrees. Using the half angle formula, that becomes the square root of 1, I have to look it up, 1 minus cosine of 2 theta divided by, or 2, sorry, not 2 theta, my bad, of alpha, which is 45, over 2. And because we're in the first quadrant, this is going to be a positive value. All right, so the square root of 1 minus square root of 2 over 2 divided by 2. And with a little bit of algebra, we simplify that. The easiest way is just to multiply the top and bottom by 2, and you end up with the square root of 2 minus the square root of 2 all over 4, or the square root of 2 minus root 2 divided by 2, because you take the root of the top and the bottom. And there is your exact value for sine of 22.5. What about cosine of 165 degrees? Well, 165 degrees is 330 degrees divided by 2. So, if you let this be alpha, then you could say cosine of 330 over 2, where 330 is your alpha, is going to be plus or minus the square root of 1 plus cosine of alpha divided by 2. Now, is it positive or negative? Well, where is 165? 165 is quadrant 2. Remember, all students take calculus, so cosine is negative there. So you'll have a minus the square root of 1 plus, and cosine of 330 is square root of 3 over 2, all divided by 2. And to get rid of the complex fraction inside, I'll do the same thing I did on the last one, which was multiply the top and bottom by 2. Distribute that across. I end up with square root of 2 plus the square root of 3 all over the square root of 4, which is the square root of 2 plus square root of 3 divided by 2. In this problem, we got cosine of negative pi over 8. And of course, we recognize that pi over 8 is not in our special family of angles, but it is actually a half of one that we do know. If you take a half of pi over 4. And maybe if it's a negative, you have a negative pi over 8. So you can think of this as cosine of negative pi over 4 divided by 2. So negative pi over 4 is your alpha. So you can use your half angle formula again and have 1 plus cosine of negative pi over 4 all divided by 2. And because we are in the negative pi over 8 is going to be down, and it's not even to pi over 4, it's halfway to 45 degrees. This is quadrant 4. All students take calculus. Cosine is positive there. So this becomes the square root of 1 plus square root of 2 over 2 divided by 2, which multiply top and bottom by 2, you get square root of 2 plus the square root of 2 over square root of 4, which becomes 2 when you simplify it. In this example, we're provided the value of cosine of alpha to be negative 3/5, and we know that alpha is between pi and 3 pi over 2. Now, to do A, B, and C here, we're going to need to know the sine and the cosine. Actually, we just need to know the cosine, don't we? We need to know the cosine of this angle. But we have to also know what quadrant the angle is in. What quadrant is alpha over 2 in? That's going to tell us the sign, S-I-G-N, of our trig functions. The way that we're going to be able to tell that is from this guy right here. If alpha is between pi and 3 pi over 2, we know alpha is in quadrant 3. But that's not the quadrant that alpha over 2 is. How do you figure out what quadrant alpha over 2 is in? If you multiply this all by 1/2, you'll get pi over 2 less than alpha over 2 less than 3 pi over 4. Now pi over 2 is straight up and down, and 3 pi over 4 is right here. So alpha over 2 has to be somewhere in this range according to this formula. And that formula was given by, up here we just divided everything by 2. This means that alpha over 2 has to be in quadrant 2. Right, that's all we need to be able to do the rest of these, because now A, sine of alpha over 2 will be the square root of 1 minus cosine of alpha, all divided by 2. And it's plus or minus. And because we're in quadrant 2 and all students take calculus, sine is positive here. We'll put a plus right there. You end up with the positive square root of 1 minus the cosine of alpha, which is negative 3/5, divided by 2. I'm going to also multiply everything here by 2, and I end up with 2 plus, actually not 5. Why would I do that? So not 2. I need to multiply everything by 5. Multiplying by 5 will get rid of my complex fraction. So you get 5 when you multiply it times this 1 here. When you multiply it times this, you get just a plus 3 over 10, which is the square root of 8 over the square root of 10. Which, to simplify that, you've got to multiply by, I will go ahead and simplify it first. That's actually square root of, divide 2 out of the top and bottom, you get 4 over square root of 5. And multiply by root 5 over root 5, you get square root of 20 over 5 to rationalize the denominator. B would be cosine of alpha over 2, which would be square root of 1 plus cosine of alpha divided by 2. And it's again plus or minus because we're in the second quadrant. Cosine is negative, right? Only sine and it is positive in the quadrant 2. So you have square root of 1 plus a negative 3/5 all over 2 with a negative up front. Multiplying by 5 over 5, I get square root of 5 minus 3 over square root of 10, which is square root of 2 over square root of 10, which is square root of 1 over square root of 5, If I multiply by root 5 over root 5, I get root 5 over 5. And it's all negative. I've dropped negative somewhere in there. All these are minus. All right, I'm running out of space. I'm going to have to squeeze it in here. Hopefully you can either write on the back of one of your pages or squeeze this in somewhere. Sorry for not giving you enough space. C is tangent of 2 theta, which we know is plus or minus square root of 1 minus cosine of 2 theta, not 2 theta, alpha over 2 cosine of alpha over 1 plus cosine of alpha. This would give me, because again we're in the second quadrant, tangent is going to be negative. You're going to have a minus square root of 1 minus a negative 3/5 over 1 plus a negative 3/5. I'm going to multiply by 5 over 5 again, and I get on top, let's come down here, I get 5 plus 3 when I distribute the 5 to these two terms, and when I distribute the 5 here, I end up with 5 minus 3, which gives me square root of 8 over 2, which is negative square root of 4, which is negative 2, is the value of tangent of alpha over 2. In this last example, I'd like to demonstrate how the inverse functions can rear their ugly heads again in problems involving double angles and half angles. In this particular example, you're asked to find cosine of 2 sine inverse of 3/5. And actually, this is not all that different from a problem that we've already done. What you recognize here is that this is just some angle theta, right? When you take the sine inverse of a number, you're finding the angle such that the sine of that angle is 3/5. You also know, because you're doing sine inverse, that its output is always going to be somewhere in the right half plane. And because it's positive, we know we're in quadrant 1. Now, if I were to think of this as cosine of 2, whatever the theta is here, this is, from my double angle formula, cosine squared of theta minus sine squared of theta. So I need to know the cosine of this angle theta, and I can find it by letting the top be y and the bottom be r. So you have x squared plus y squared equals r squared, which means x squared has to be 25 minus 9, or 16. So x has to be a positive 4, and it's positive because I'm in quadrant 1. Which would mean that cosine of my angle, which is x over r, would be 4/5. So since I now know cosine of theta and sine theta for whatever theta I get out of the inverse of sine of 3/5, I can now just plug in those numbers. This is going to be 4/5 squared minus 3/5 squared, or 16/25 minus 9/25, which gives me 7/25. Not all that different from a problem we did earlier, only it's written a different way. It now involves inverse trig functions. The last thing I think we should look at out of this section is the fact that there is an alternative half angle formula for tangent, and it kind of comes from a surprising manipulation of your other half angle formulas. We derived one that said tangent of alpha over 2 is plus or minus the square root of 1 minus cosine of alpha over 1 plus cosine of alpha. And we derived it straight from the other half angle formulas. But with a little bit of just playing around algebraically with our identities, we can show that tangent of alpha over 2 can actually be written as one of these two expressions. And it's always true. And notice the beauty of this is that there are no plus or minuses. When the plus or minuses are in there, you have to go and do extra work to find what quadrant you're actually in. This is true no matter what alpha would be. So why is this true? Well, recall that cosine of 2 theta is 1 minus sine squared of theta. That's where I'm going to start. And as we did before, let's let theta Actually, let's let 2 theta be alpha, which means that theta now is alpha over 2. So if I use this and rewrite this equation, this identity, I have cosine of alpha equals 1 minus sine squared of alpha over 2. Which means that, I'm sorry, I got a 2 missing. There's a 2 here, and there's a 2 here. That I've got 2 sine squared of alpha over 2 is a 1 minus cosine of alpha. Now, how did I get that? I moved the, I'll tell you what, let me just rewrite it this way. Let's move the 2 sine squared of alpha over this way and the cosine of alpha over this way. So you have 2 sine squared of alpha over 2 is going to be 1 minus cosine of alpha. Now, if you don't see where I'm going, that's fine. Just believe, or at least make sure you can verify that what I have just written is in fact true, simply because we started with a cosine double angle formula that we've already proved, and we replaced 2 theta with alpha and theta with alpha over 2, and then just moved things around in the equation. Now, also, we know that sine of 2 theta is 2 sine theta cosine theta, which would mean sine of alpha is 2 sine of alpha over 2 cosine of alpha over 2. So what I want us to do is consider this formula right here, using the 2 identities that I just derived. That is, what is 1 minus cosine of alpha over sine of alpha? Well, cosine of alpha, according to this, is 1 minus 2 sine squared of alpha over 2. And on bottom, sine of alpha is 2 sine of alpha over 2 cosine of alpha over 2. Now, if I distribute my minus sign on top, I'll have a 1 minus 1 plus 2 sine of alpha over 2 divided by 2 sine of alpha over 2 cosine of alpha over 2. Now, the 1 minus 1, subtract out, the 2's will divide each other out, as will the sine of alpha over 2, well, one of them will. All right, and so you're left with sine of alpha over 2 over cosine of alpha over 2, which is, in fact, tangent of alpha over 2, proved. Now, we proved the yellow one. To prove the one that's in blue is exactly the same procedure. Just start with that equation, plug in your 2 identities, and you will see that you do, in fact, get tangent of alpha over 2. All right, that's the end of lecture 21.